So in this lecture, we see the topic Eulers and Fermats theorem. So first we see statement of that Eulers theorem. If an integer a is relatively prime to natural number n, then a raised to phi n is congruent to 1 modulo n, where phi is nothing but the Euler's Torsion function. So here a is relatively prime to n, that is GCD of a and n is equal to 1. Then we have to show a raised to phi n is congruent to 1 modulo n. Here phi is nothing but the Euler Torsion function, so that we have studied to calculate that group Zn dash. You see the proof of this one. So we know that Zn dash is nothing but the set of all a bar belongs to Zn, such that GCD of a and n is equal to 1. Means here it is the group of all prime residue classes modulo n. So we have seen the example of Zn dash. It contains elements 1 bar, 3 bar, 5 bar, and 7 bar, because 1, 3, 5, 7 have GCD 1 with that 8. So Zn dash contains those number of elements whose GCD with n is equal to 1. So number of elements in Zn dash are same as that of elements in phi n. So thus here order of Zn dash is equal to phi n. So let GCD of a and n is equal to 1. Now GCD of n is equal to 1. So therefore a bar belongs to Zn dash. So a bar belongs to Zn dash. So we know one result, that is if a is an element of a finite group G, then a raised to order of G is equal to identity. So by using that result, order of G is nothing but order of Zn dash, that is equal to phi n. So here we get the result, that is a bar raised to phi n is equal to identity element in that multiplicative group, that is 1 bar. So a bar raised to phi n is equal to 1. So thus a raised to phi n is congruent to 1 modulo n. So here we have the modulo n operation. So we get the result, that is a raised to phi n is congruent to 1 modulo n. So whenever GCD of n, a and n is equal to 1, then we have this one is Euler's theorem. Now next one is Fermat's theorem. So Fermat's theorem is for prime number p. So if p is a prime number and a is an integer such that p does not divide, say, means here again GCD of a and p is equal to 1 because p is prime number, then here we have to show a raised to p minus 1 is congruent to 1 modulo p. So here we use that Euler's theorem. So proof of this theorem, let p is a prime number and a belongs to z such that p does not divides a. So from that we can say GCD of a and p is equal to 1. So from that we use the Fermat's theorem. So by Fermat's theorem we have we use that Euler's theorem. So in Euler's theorem we have a raised to pi p is congruent to 1 modulo p. But here p is prime number and we know that value of pi p, because p is prime number, GCD with all less than or equal to p are equal to 1 except p. So value of pi p is p minus 1. So we replace that pi p by p minus 1 because p is prime number. So thus we get the result, that is a raised to p minus 1 is congruent to 1 modulo p. So this is the Fermat's theorem. So these two theorems are important. So in the Euler's theorem we have seen a raised to phi n is congruent to 1 modulo n whenever GCD of a and n is equal to 1. Note that here n may not be prime number. Here n is any natural number. But in that Euler Fermat's theorem, p is prime number. Then in that case we have a raised to p minus 1 is congruent to 1 modulo p. Now we see the examples depends on this Euler's and Fermat's theorem. So find the remainder obtained when 3 raised to 54 is divided by 11. So 3 raised to 54 is divided by 11. So note that here 11 is prime number. So we can use the Fermat's theorem. So here 11 is prime number and 11 does not divide 3. So therefore by Fermat's theorem 3 raised to 11 minus 1 is congruent to 1 modulo 11, because by Fermat's theorem we have 3 raised to p minus 1 is congruent to 1 modulo p. So 3 raised to 11 minus 1 congruent to 1 modulo 11. But 11 minus 1 is 10. So we get 3 raised to 10 is congruent to 1 modulo 11. Now we require 3 raised to 54. So we take the fifth power on both sides. So therefore 3 raised to 10 raised to 5 is congruent to 1 raised to 5 modulo 11. So from that we have 3 raised to 10 raised to 5 means it is 3 raised to 50 and 1 raised to 5 is 1. So we get 3 raised to 50 is congruent to 1 modulo 11. Now we require 3 raised to 4. So 3 raised to 4 modulo 11. So we know that 3 raised to 4 is equal to 81. 3 raised to 4 is 81 and modulo 11, that is if we divide 81 by 11, then remainder is 4, sorry, because 11 7s are 77, 81 minus 77 is 4. So 3 raised to 4 is congruent to 4 modulo 11. Take the product of equation 1 and 2. So from equation 1 and 2, we get 3 raised to 50 into 3 raised to 4. 3 raised to 50 into 3 raised to 4 is congruent to 1 into 4, that is 4 modulo 11. But 3 raised to 50 into 3 raised to 4 is 3 raised to 54. So therefore we get 3 raised to 54 is congruent to 4 modulo 11. It means that when we divide 3 raised to 54 by 11, the remainder is 4. So thus 4 is the remainder obtained when 3 raised to 54 is divided by 11. Then next example, find the remainder obtained when 41 raised to 65 is divided by 7. Again here 7 is a prime number, so we use that Fermats theorem. So here 7 is a prime number and 7 does not divide 41. So by Fermat's theorem, 41 raised to 7 minus 1 is congruent to 1 modulo 7. That is 41 raised to 6 is congruent to 1 modulo 7. Now we required 41 raised to 65. So we take the 10th power of this one to get 41 raised to 60. So therefore 41 raised to 6 raised to 10 is congruent to 1 raised to 10 modulo 7. But 41 raised to 6 raised to 10 is nothing but 41 raised to 60, and 1 raised to 10 is 1. So thus we get 41 raised to 60 is congruent to 1 modulo 7. Now we required 41 raised to 65, means here we have to multiply by 41 raised to 5. याला आपल्याला 41 raised to 5 ने multiply करावं लागेल. So we know that 41 is congruent to minus 1 modulo 7. 41 is congruent to minus 1 modulo 7. Because it is 42, 42 is congruent to minus 1 modulo 7. So 41 is congruent to minus 1 modulo 7. So take the fifth power on both sides. So that 41 raised to 5 is congruent to minus 1 raised to 5. 41 raised to 5 is equal to minus 1 raised to 5, that congruent to minus 1 modulo 7, because minus 1 raised to 5 is minus 1. So here we have, but minus 1 modulo 7 is nothing but 6. Current means here we know that minus 1 is congruent to 6 modulo 7, because minus 1 minus 6, that is equal to minus 7 is completely divisible by 7. So minus 1 is congruent to 6 modulo 7. So here we replace this minus 1 by 6. So thus from equation 1 and 2, if you multiply these two equations, then we get 41 raised to 60 into 41 raised to 5 is congruent to 1 into minus 1, that is minus 1, but minus 1 is nothing but 6. So thus 41 raised to 65, this left hand side is congruent to 6 modulo 7, and 6 is the remainder when we divide 41 raised to 65 by 7. The next example, find the remainder obtained when 15 raised to 27 is divided by 8. So here 8 is not prime number, so here we cannot use that Fermat's theorem, so here we use that Eulers theorem. So let n is equal to 8 and a is equal to 15. So here GCD of that 8 and 15 is 1. So and we have phi of n, that is phi of 8 is equal to 4. So that we know, because we know that phi of 8 means here it contains elements of z dash, that is 1 3 5 7. So whose GCD with 8 is 1. So 1 3 5 7, in all there are 4 elements, so phi of 8 is equal to 4. And here GCD of a and n is equal to 1. So here we use that Euler's theorem. So that by Euler's theorem, a raised to phi n is congruent to 1 modulo n, but phi n is equal to 4 and n is equal to 8. So thus here we have 15 raised to phi 8 is congruent to 1 modulo 8, that is 15 raised to 4 is congruent to 1 modulo 8. Now here we required 15 raised to 27. So here we take the power raised to 6. So therefore 15 raised to 4 raised to 6 is congruent to 1 raised to 6 modulo 8, but 1 raised to 6 is 1, and 15 raised to 4 raised to 6 is 15 raised to 24. So thus we get 15 raised to 24 is congruent to 1 modulo 8. Now we required 15 raised to 27, and here we get 15 raised to 24. So just we have to multiply by 15 raised to 3 to get 15 raised to 27. So we know that again 15 is congruent to 7 modulo 8. 15 is congruent to 7 modulo n. So therefore 15 raised to 3 is congruent to 7 raised to 3. So 7 raised to 3 is 343. And when we divide 343 by 8, the remainder is 7. That is 343 is congruent to 7 modulo 8. म्हणजे 343 ला 8 ने डिवाइड केल्यानंतर रिमाइंडर किती आहे 7. Now here we multiply equation 1 and 2. So on the left hand side we have 15 raised to 24 into 15 raised to 3, that is 15 raised to 27 is congruent to 1 into 7, that is 7 modulo 8. So therefore 15 raised to 27 is congruent to 7 modulo 8. So thus here 7 is the remainder when we divide 15 raised to 27 by 8. Okay.